All right, guys, in this video, we're going to be looking at some intermolecular forces questions. In this first one, the structural formulas of two compounds that are liquids at room temperature are shown above. Which of the following statements best explains the observation that compound 1 boils at 35 degrees Celsius, whereas structural isomer compound 2 boils at 118 degrees Celsius? Okay, first off, isomer just means same. So these are going to be like compounds with the same amount of carbons, oxygens, and hydrogens, but their structures are different. And because of that, they're going to have different intermolecular forces. Now, compound 1 boils at 35 degrees Celsius, and compound 2 boils at 118 degrees Celsius. Before even answering like which one has stronger intermolecular forces, I would think that compound 2 is going to have stronger IMFs. Okay, the reason why I think that is because it has a higher boiling point. Remember, in order for it to boil, we have to break those intermolecular forces. So if it's got a higher boiling point, it's going to have stronger intermolecular forces. If it has a lower boiling point, it must have weaker IMFs. So now I'll look at the structures and determine if that's true. First off, all molecules should do dispersion forces. And since these have the same molecular formula, those dispersion forces are going to cancel each other out. They have the same amount of atoms, so they're going to have the same polarizable clouds that they can form. Looking at these two, this one on the left appears to be nonpolar, but actually this oxygen on the middle, even though they don't put it in there, it's got two lone pairs on it. And that's going to cause a bent shape at this oxygen, and therefore this is actually going to be a polar molecule. And that may be hard to see at first, but that is how this molecule is going to look. This is a polar molecule, so it will have dipole-dipole forces. Looking at this molecule, because of this OH over here, it is also polar, and it forms dipole-dipole forces. But we also talked about if there is an oxygen, fluorine, or nitrogen bond to a hydrogen, it also does hydrogen bonding. Whereas on the compound 1, there is no hydrogen attached to this, so it cannot do hydrogen bonding. Therefore, compound 2 has stronger IMFs because it can do hydrogen bonding, and that's why it has a higher boiling point. So looking at these answer choices, and you can read through them all, but the answer will be D. Although there are dipole-dipole attractions among molecules of both compound 1 and 2, the OH group in compound 2 allows stronger hydrogen bonding to occur. Okay, for this next question, we've got a table of ions and their radiuses, or radii, I don't know how you say it. Based on Coulomb's law and the information in the table above, which of the following anions is most likely to have the strongest interactions with water molecules in an aqueous solution? Okay, so there's two factors that are going to affect the strength of attraction to a water molecule. Okay, and that is the charge of the ion and the distance of the ion. Okay, in this case, the higher the charge, the stronger that interaction is going to be. So looking at my 4 ions, I can already count out chlorine and iodine because they only have -1 charges. They're not going to be as strong of an interaction. The other factor now is the distance. So the closer this radius, or closer that ion can get to the water molecule, the stronger that interaction is going to be, right? We learned that in Coulomb's law, the higher the charge and the smaller the distance, the stronger the interaction. So comparing these two radiuses, or radii, we're going to choose one that's a smaller radius. So I think answer is going to be C, solely based on the fact that these two have higher charges compared to the first two. So this one and this one. But between distance, this one's bigger, so it's not going to be right. So this one has the best chance of having the strongest interactions. All right, one last one. PP is synthesized from propene. C3H6, and PVC is synthesized from vinyl chloride, C2H3Cl. The structures of the molecules are shown below. The boiling point of liquid propene, 226 Kelvin, is lower than the boiling point of liquid vinyl chloride, 260. Count for this difference in types and strengths of intermolecular forces present in each liquid. So this one is at 226 Kelvin, and it is lower than vinyl chloride, which is at 260 Kelvin. So right off the bat, we know since vinyl chloride has a higher boiling point, this must have stronger IMFs. And this one will have lower IMFs, or weaker IMFs. And now let's identify them. So looking at propene, first off, all I see are carbons and hydrogens. Okay, carbons and hydrogens have essentially the same electronegativity, and therefore, if there's just carbon and hydrogen, this is a nonpolar molecule. And since it is nonpolar, it can only do dispersion forces. Okay, whereas this one over here has this chlorine attached to it, and then carbons and hydrogens. And because of this chlorine and where it is, this can form a dipole. And we will have electrons being pulled to this side, leaving this side positively charged or partially positive charged. So we have dipole-dipole interactions as well as dispersion forces. Okay, it can't do any hydrogen bonding because the hydrogens here are bonded to the carbons and those don't count. It has to be to an oxygen, fluorine, or nitrogen. So the boiling point will be higher because it has dipole-dipole interactions because it is a polar molecule. Whereas the propene can only do dispersion forces because it's a nonpolar molecule. So somewhere in your, if this was a short answer, you would have to explain that using all of these things. So write it out really nice and clear, the reasons and why the strength, or talking about the types and the strengths of those intermolecular forces in each liquid, and why one will have a higher boiling point than the other.